Hello friends, so today we're going to discuss the fifth problem from the AtCoder beginner contest 187, problem name through path. So I'll just move through the whole question first and then we're going to discuss the tutorial and then the code itself. So the problem statement states that we have a tree with n vertices and n-1 edges, and as you know, and any tree has n vertices and n-1 edges. If you don't write a tree, you can obviously understand that this is a tree. Second point, in a tree there's always like a single path from any two nodes. Like there's also one property of tree that if you take any two nodes in a tree, then there always exists only one path from one node to another node. Okay, so as you can see, the vertices are numbered from 1 till n, and also the edges are numbered from 1 till n-1. Edge I connects the vertex, like vertices ai and bi. So as you can see, the vertex and the edges are also given numbers, and the ith edge connect the ai and bi. As you can see in the input, the ith edge connect and they are n-1 edges, so the connections are given to you. Now there are q queries, and each query you are given ti, e of I and x of I. Now how this query works, if the type of the query is 1, then what will happen here is, for each vertex v reachable from a of ei without visiting the vertex b of ei but traversing edges, replace cv with cv plus xi. Okay, so now there's also one more line here, is that every vertex in that tree has some integer written on it, and initially all the values written on that tree is 0. So I'll draw the first example to even make it more clear. So as you can see, the first example states that there are 5 nodes, one, and there's one edge from 1 to 2, as you can see here. Then there is from 2 to 3, so 2 to 3 like this. Then there is from 2 to 4, so 2 to 4 like this. And then there is from 4 to 5, so 4 to 5. This is the some sort of tree. Okay, so now what the problem statement states that in the ith query, if the query is of type t1, then for every vertex v reachable from the vertex a of ei without visiting the vertex b of I but traversing the edge, replace cv plus xi. So what does this mean here is that if you are given that every edge has some number now, 1 2 3 4 5. Now in this problem, if they tell that e of I, the a of 1 and b of 1, it just means that if e of I equal to 1, that it means that for each vertex v reachable from the vertex a1 without visiting b1, which means that for all the vertex, if I just take out, let's assume that if I take this edge and there's an edge between 2 and 3, then what does this mean here is that all the vertex which are reachable from 2 without reaching 3 should be increased, those values should be increased by xi. As you can see, all these nodes can be reached by 2 without reaching 3, and thus the value should be increased by xi. And you have to do like these types of queries, in which if there's a edge from ai to bi or bi to ai, you just have to ignore one thing. Now as you can see, if there is some tree like this, and because if I want to reach from this node to all these nodes, then I have to go through this node, like this node, and because these nodes are connected, then and the constraint states that I cannot travel between these two nodes, like this node is prohibited, so I cannot travel through this node. So all the nodes which are below this node will not be traveled, and thus all the nodes except all these nodes should be traveled. And thus that's the problem statement. You are given these types of queries, and you have to mark out and find out the final value on all of the vertex after these queries processing. Now I'll even make it more clear with the example, understanding the question, and then we'll go through the problem statement or the code. But so as you can see, this is the diagram I've drawn, and then there is the type 1 query. Type 1 query means that for the first edge is this edge, which means that this 1 and 2 edge is the first edge. You have to add 1 to all the nodes, in which you can reach all the nodes except 2. So one type of node query means that I have to reach to all the vertex from a of I, which means the first from 1 I have to reach all the vertex without traveling to the vertex bi. So if from 1 I want to reach all the vertex without traveling to 2, I cannot reach because I will always travel to 2. So the only value the only node whose value will increase will be this node, because this is the current node on which we are. So the value will increase by xi. The xi for the first problem is 1. So this value will become 1 and all will remain to 0. Now as you can see, the second is the fourth edge, 1 2 3 4. This is the fourth edge, which is like this edge 4 and 5. This is 4 and 5. So now the problem statement states that if you want to go from 4 to every node except the node which consists of 5, then increase all the nodes value by 10. Now as you can see in this problem statement, if all the nodes except, because if I go down then I will go all the nodes which are having 5, but if I go up then it's fine, and thus the answer of all these nodes, this will increase by 10, this will increase by 10, this will increase by 10, and this will increase by 10. I hope you get my point. Now the next is the second type of operation, but of type like this from the first node. This is 1 2, which means that now from, so if the second type of node, then we have to think that if all the nodes which are reachable from 2 except the paths will take from 1. So as you can see, from 2, if I don't go up, then these nodes will increase the value, which is like the value will increase by 100. I think so. Yeah. So now I will increase all the value by 100 and so on. So I hope you get my point, how we are like finding out of how this question is working. We are given a particular edge, and from like, and the type of query, if the type of query is 1, then we'll take the first edge node, find out all the like nodes which we can reach except the path which travel through this node, and thus it means that all the nodes which will be along this path will not be reached, all the other nodes should be reached, and all the values of those nodes should be increased by this xi, and then after all the processing, find out the final value on the vertices. And that's the whole problem. Now this problem seems difficult, but there is like 2 tricks or 2 like observations you have to make, and then the problem becomes easy. So in such type of problem, you'll always, or like if you know that there is some problem in which like an array type, if you want to increase some values in the array, maybe from this sector, from this part, or from this part, or from this part, if there are like q queries and you want to increase the value of the array from this to this point, this to this point, in like O of like they are q queries, then if you do an O of n operation on the sections, then it will be a O of n square. Then what you can do here is just mark out the query and O of n. So if you want to increase the value from this to this point, then increase this by 1 and put this with -1. If you want to increase this and this, then like put this one with 1 and increase this with -1, and then go in O of n and mark out all the values, and then you can easily find out all the values in O of n. So okay, you will not do O of n square. And same will do this in this in this tree also. We'll try to mark out all the nodes which will be processed. So for every, so as you can see, for every edge, as you can see, like for every node, if I want to take this edge, if I want to like discuss about these 2 nodes, then either I have to mark out all the nodes which are above this node, or all the nodes which are below this node. I hope you get my point. If I will take this edge and the path will be this, which is like I want to take out this node, and I want to don't go through the nodes along this path, then I will mark out all the nodes which are like above this, like this, or like this part, but not along this path. I hope you get my point. And if I want to mark out all the nodes like above this, just take out, then all the nodes above this should be marked. So for all the nodes, it is like if it is above or it is below. Now how you can find out, and how you can use this technique. Now how you can find out here is, if let's assume that I want to take this edge. If I take this edge and I want to find out how many edges, or like in how many nodes I want to add. Now what you can easily do here is, if I do a traversal from top to the root to any edge, okay, if I find out that I want to add all the values below this node by a value of 10, then I just put 10 on the root node, and all the edges below it should be incremented by 10, or like all the nodes below that should be incremented by 10, because there's one type of query in which all the nodes above should not be marked, which means that if I want to take this node and the above node is cancelled, then all the nodes below it should be marked. So what I can do here is, I can just mark out this node value with that original value, let's assume 10, and whenever I hit this point, all the nodes below it should be marked or incremented by 10, and above will not be incremented. And But the vice versa, if I want to increase all the values above this node, then what I can do here is I can do the same thing. What I can do, I will increment, like if I want to increment all the values above this node with 10, then I will make 10 incremented on the root. Then all the values till this point will be incremented by 10, but after this point I don't want to be 10, so I will put minus 10 at this point. So that's what I'm saying, like increment the starting point with 1 and the ending point with minus 1, and that's what I've done. If I want to increment all the values above this node to be 10, then what will I do? I will mark out the 10 with the root node, like the top node, 0th node, and then because on which I will start the DFS or BFS, whatever I will do, and then all the nodes below this minus 10, like below this root, which I don't want to mark because that path is cancelled, then put minus 10 or the minus x value at that point. And thus when I will do a, so now it just like drop down to a BFS or DFS, and then what you'll do whenever you run a BFS, or like you can do in a BFS, because that will help you to mark down in a level order traversal. In level order traversal, because you have to find out what are the nodes above it or below it, because if it's above it, what you can do is just mark out in a level order traversal in a BFS, and if it is above it, then what you can do, you can just mark out all the nodes, and whenever you reach some point in which as you can see after this node you want to just minus 10, so just minus 10 and all the values will be filled in O of n only. I hope you get the intuition of this problem. What you can do, I can try run on some like test case to even make it more clear. So what you can do here is there is like 2 points you have to also tell. I'll also tell you with the first example only. So I'll try run the first example. So as you can see in this problem, just remove all the values. I'll find out the values from start. So what you can see here is, in the first value I want to increase the first edge, which is 1 and 2, and increment all the values, all the nodes which are not reached from like 2, like from 1 till 2, as you can see. So what all the nodes below this should not be incremented. So what I can do, I can increment the root node with 10 and the base node with minus 10, the minus like this 2, and thus whenever I do like bottom or like a level or traversal, this node will be given 10. The total accumulation till now is 10. Now the next point, the total accumulation becomes 0 and 0 and 0, and as you can see the first node will only get incremented by 10 and the rest will not increment, right? And that's what we want, because all the nodes above this should be incremented, not below it. The next thing, as you can see, there's also of the fourth edges, which is from 4 to 5, which means from 4 to 5 all the edges below this should not be incremented, but all the edges above 4 should be incremented. So what, this should be incremented at 100. So increment the first node with 100 and this node with minus 100. Okay, and then as you can see, this is the third point, the first edge, this is by 100. Like as you can see, all the nodes, the first two from 1 and 2, so all the edges like this is from 1 2, so like from starting from 2, all the edges below it. So as you can see, I want to mark all the edges below it. So what I can do, just mark out the current value with 100 value, because when I will come down from this point of view, all the nodes below this should be incremented by 1000. And this is also the second node, like this is second edge from 2 to 3, so from 2 to 3, so all the edges above this should be marked out. So as you can see, all the edges above it. So what I can do, if I want to mark out above edges, mark out the root with like maybe this is 100 or like 1000, I don't know, maybe like x, and all the nodes below it should be minus x, and then just run out a BFS from the first node. Sorry, mark out the first values, what are the cumulative sum for the first node, maybe it's like y1, then go to the next node, y1 plus this cumulative sum will be the y2, then y2 plus this cumulative sum will be the next node and next node and so on. And that's how you will, I will tell you more with the code, and then it will become more easy. I will also link down the code in the description so you can see it out also. So this is n, this is the input of the total number of like nodes. This is for storing out the edge, like I think so this is for the edges because there are n-1 edges. This is for storing out the adjacency matrix or adjacency list for the at the graph or the tree, whatever you can call. Then this is the storing of the like the edges, and -1 because I want to make the edges from 0th indexing. The question has 1th indexing, and then make the adjacency list bidirectional. Then I want to find out the depth for every node. So I will finding out a depth for every node using BFS. So as you can see, the top node, the 0th node is given like the 0th like depth 0, and then for all the other nodes, as you can see, first push back, make a queue, push back the 0th node in the the queue, and till the queue become empty, pop out the first element, and then iterate over all its children. If its depth is not counted because I have initialized all the values -1, it means that I have not found out the depth for the current node. Mark the current node depth is current, the top node, the parent node +1, and then push that node in the queue itself and just output. Then the whole the depth of all the nodes are stored in this D. Then what we'll do, then iterate over all the queries is of type E and X. Okay, then there is one thing. Okay, so there's one thing in this problem which you have to think. I can tell you. Yeah, so as you can see, the thing here is, as you can see, this is of type 1 node, like this node is of type 1. And now what you can think in this problem is, because if this is type 1, all the vertices of AI without visiting BI. So if, as you can see, if I am on this node and I want to go through this node, which means that from AI till BI, maybe that there is AI is this value, this is because I have counted out the depth. Okay, this representation I have given according to the assumptions I have made, that the edges is made like that 1 is above, 2 is on the second depth, 3 is on the third depth, 4, 5, and so on. But now it can also happen that the edge might be like this, 1, 2, and 3, 2. Then in that case you will draw the tree like this, 1, 3, and 2, and the whole tree will changed. I hope you get my point. And thus you have to also ensure that my depth, my total path should always remain the same. It always, because my assumption is, if I take any edge, the first edge should be in a depth lower than the next depth, because as you can see, the next depth is higher, this is more deeper than this depth. So the edges which I have taken, it should be in such a manner that the depth of the other node, the first node, should be smaller than the next depth. But it might happen that the depth we have calculated might be up reversed, because it might happen that the edges we have taken might not be in the same manner, which I tell that it can happen that this third has a depth which is smaller than the second depth, but that will violate our assumptions. We are taking that whenever I will take out this TI or the type I, there are two types, whether I will mark out all the above edges or the below edges. But in that case I have to also ensure that the top edge or this edge should have a lesser depth than the next depth, the current depth or the neighbor depth, and thus you have to also ensure that. So that's what I've done. These are the two. So for the type, we have to find out what for this this edge, the edge number. So because the edge is from 1th indexing, I will also make them the 0th indexing, so E -1. Find out the edges, the nodes which is connected by 2 edge, but because as you can see, if I want to take the 4th edge, then what are the nodes connected by this? This is 4 and 5. So that's what we have found out. This 4 and 5 are connected by this edge. I have to find out that the first depth, or the depth of the first node, should be smaller. If it is greater, then swap them out. Just swap them out, and also swap their type. Okay, because not just swap their numbers, but also swap their type. So 1 should become 2 and 2 should become 1. So that's what we have done, because the XOR of 1, 2, 3, the XOR of 1 and 3 will equal to 2, and XOR of 2 and 3 is equal to 1. So that's what we have done. It's just swapping the numbers and swapping their type. It's necessary because we always want that the first number should be smaller in depth than compared to second number. And that after we have done, we have two types, the first and second. In the first type, all the nodes above should be marked, And the second type, all the numbers below should be marked. If all the numbers above should be marked, then what we do, we'll mark out the root node, which is like marking out with +1, like +x, and the root below this, or the current node, like b value, with -x, which I've told you in the example. And in the next part, what you can do, if the type is of other type, then what you can do, just mark out the current b node with x, +x. So if you want to mark all the nodes above it, mark out the root node with +x and the current node with -x. If you want to mark out all the nodes below it, just mark out the like the current node with +x. Yeah, and then do the same DFS starting from the root node. That's what we have done. And take the root node, and for every other children, if you want to take the root node as the current value, for all the root nodes below it, take down if the depth is greater, because we don't want to go above. It's just that you can also check that if the current node is not the parent of itself, just don't process the parent, just go to downwards. You can check this, or you can check that if I is not the parent itself, just you can do anything. If that will happen, the answer of I is the answer of I plus its parent value, because I'm just doing a cumulative sum, what I've told you. Like for every value, just every node, if you go to the next level, just take out that sum and add it to it. I've drawn the example of the array, that's the same thing. And then just push back the new value, and it's just a simple DFS, a simple BFS, sorry, using the cumulative sums. And then you just output all the node values. It's a little bit confusing, but if you understand the logic part and the code part, it becomes very simple. If you even understand the logic part, how to implement this, if you still have any doubts, you can mention down in the comment box. I'll see you next one. Keep coding. Bye.